Loading the libraries. Now we'll set the current directory to the working directory. We'll import the CSV file. Now we'll start the EDA. Viewing the database structure, we can see that all variables are numeric apart from the target variable. We can view the dimensions. We can see the overall class distribution, that it's unbalanced, in fact almost to 91%. We'll have a look and see that there's no missing values. In the first 20 rows we can see that we're going to need to scale the data so that it's all in the same format. We can see there's quite a bit of difference in the distribution of some of the variables. Now we'll have a look at the data visualizations. We'll have a look at the histograms. And then clear it. Then we'll have a look at the density plot. We can see in a few variables we've got a right skew. Clear it. Box plots, we can see quite a bit of overlap between them, with a lot of outliers, which are going to make it difficult to remove them. Clear it. Now we'll have a look at the scatter plot matrix. We can see quite a bit of good separation between the classes. We'll clear it. Now we'll try correlation plot. We see several of the variables have quite high correlations. Now we'll clear it. Now we'll start the pre-processing. We'll set the seed and we'll shuffle the data. Create the train test split by creating the split indices of 70-30. Create the training and validation sets. Separate the features and target from the training set. Separate the features and target from the validation set. We'll scale xtrain. We'll convert to a data frame and add the class. Separate the majority and minority classes before performing random upsampling to the minority class. Then we'll combine the majority and the upsampled minority class. We'll shuffle the balanced data set before verifying that the class distribution has indeed been upsampled and that Y-train has been untouched. We'll convert it back to a data frame. We'll ensure that Y validation is a factor with the same levels. Now we'll start the training. We'll start with the logistic regression and our baseline will be GLM. We'll start with the train control, which is tenfold cross-validation with 3 dip repeats. Train the model with a cross-validation. We'll print some results. Now we'll make predictions on the validation set, create the confusion matrix. We can see we have an accuracy of 97.06. We have 45 false positives and 113 false negatives. Sensitivity, which are non-pulsars, are quite a bit higher than the actual pulsars detected. And with the cross-validation already imported, we'll try GLMnet. We'll import it. We'll print some results, which the plot can show that smaller regularization strength gives better results, and it's leaning towards a lasso regression being better. Now we'll print some best tuning parameters to use in the future to guide us. Now we'll make predictions using the confusion matrix. Now we can see that we have less false negatives but the same false positives. We've got higher accuracy, better kappa and better sensitivity. Now we'll use GLMnet with ridge regression. I've set up a tuning grid. We'll import that. Now we'll train it. Print the summary and the best settings. Now we'll make the predictions, create the confusion matrix and print it out. And we can see here that we've got more false positives, more false negatives, lower accuracy and a lower kappa, which is to be expected. Now we'll test GLMnet lasso. I've tuned it. It's got the alpha of 1 hard coded and the best lambda from testing, very low. We'll import that. Now we'll set the seed and train the model. We'll print the summary, make the predictions, create the confusion matrix and print it. And we can see that lasso has the highest accuracy so far. It has the best kappa. It has less false positives, though it has slightly more false negatives than GLM or GLMnet. Next we'll test GLMnet with ElasticNet. I found a best alpha of 0.5 to 0.8 by 0.3. The lambda sequence is 0.3, 0.1 to 0.001 with a length of 10. Import that. Now we'll train the tuned model. Now we'll print out the summary, the plot, and print out the best settings. Now we'll make the predictions, and we'll create the confusion matrix and print it. And we can see that ElasticNet has the second best accuracy out of all the models. It has a very good kappa, best specificity, and it's got a better overall balance of the metrics. Now we'll try our second model, K nearest neighbour. I'll load the train control, 10 cross validation with 3 repeats. I'll load the model, train it. Now I'll print the summary, make the predictions, create the confusion matrix and print it. And we can see that K nearest neighbour by default has the lowest accuracy, lower kappa, highest false positives, although it has lower false negatives than the other models. Now I'll try K nearest neighbour with a tuning grid. We'll try K from a sequence of 1 to 30 by steps of 1 to see what the best settings are. We'll train the model, and then we'll print the summary, plot the model, and print the best results. And it's shown us that a K of 13 would be the best results. We'll make the predictions, create the confusion matrix, and print it out. We can see here that so far we've got the lowest accuracy, the highest false positives yet, the lowest kappa yet, although we do have the lowest false negatives. Now we'll try K nearest neighbour with a K of 13. We'll import that, train the model, print the summary, make predictions, create the confusion matrix and print it. And we can see that it's slightly better than tuned, though it has worse false negatives than the untuned K nearest neighbour. Our next model is SVM with a radial kernel. We're going to use a tuning grid to search for this best sigma of we're going to start at 0.01 to 2 with a length of 5, and the C search will be 0.01 to 5 with a length of 5, equaling 25. Next we'll be doing cross validation of 10, so I'll set them away and tune the model. Now we'll print the plot, the summary and the best values. We'll train the model with the best parameters, make predictions on the final model with a validation set, create the confusion matrix and print it out. And we can see that SVM with a radial kernel has the highest accuracy, the best kappa and the fewest false positives. We can also see from the plot that it's all one colour and that the best performance is a very low value. Our next model is SVM with a linear kernel. It has a tuning grade of C with 0.1 to 2 with a length of 5. So I'll run the tuning grid, I'll tune the model, then we'll plot the model, print the summary. We can see that change in C has very little effect on the model. Now we'll train the model, make the final predictions, create and print the confusion matrix, and we can see that it's 97.49. It's very slightly lower than radial was. Now I'll try a final model. It'll be random forest at first without a tuning grid, so I'll load the model. Now I'll print the model and plot the results. Now we'll make predictions on the validation set, create the confusion matrix and print it out. And we can see that apart from specificity, we got the higher accuracy and all the other metrics are higher than previous models. Finally, we'll try random forest with a tuning grid. We'll load the cross validation parameters. We'll use a tuning grid of 1 to 8 by 1 for the M-try. We'll train the model. I have an entry of 80, node size of 2 and max nodes are 1000. These are the optimal settings. Now we'll print the model, create the best M-try, print the best M-try, plot the model results. Now we'll make predictions in the validation set, create the confusion matrix and print it out. And we can see that we have the highest score yet of 98.34 for accuracy. All apart from specificity are the highest we've had so far across all models. With that, random forest with the tuning grid has been chosen as a final model.